Let us look at some theorems on limits of sequences. The first one is uniqueness of limit. That means if a limit exists for a sequence, then it is unique. So let limit as n goes to infinity of a sub n is equal to L1. And let's assume that limit as n goes to infinity of a sub n is equal to L2, where L1 is not equal to L2. So we are assuming that the sequence a sub n has two distinct limits, L1 and L2. Now let's take the epsilon equal to the midpoint of L1 and L2 and take the magnitude of that. And this is greater than 0. Because if they are not equal, that means there is a value here. Divided by 2 will give us the midpoint. And since we are taking the absolute value, it is going to be greater than 0. Since L1 is a limit of a sub n, that means there exists n1 in natural numbers such that the magnitude of a sub n minus L1 is less than epsilon for all n greater than n1. So at some point in the sequence, the magnitude of the difference a sub n minus L1 will become less than epsilon. Similarly, because there is another limit also, there exists n2 in natural numbers such that the magnitude of a sub n minus L2 is less than epsilon for all n greater than n sub 2. So let n be the larger of these two, n1 and n2. Then for all n greater than n, we have the magnitude of L1 minus L2 is equal to the magnitude of L1 minus An plus A sub n minus L2. Remember, this is for all n greater than n. Now, remember this. Magnitude of x plus y is less than or equal to magnitude of x plus magnitude of y. So, same thing we apply it here. We get magnitude of L1 minus An plus An minus L2 is less than or equal to the magnitude of L1 minus An plus magnitude of An minus L2. Magnitude of L1 minus An plus magnitude of An minus L2 is less than 2 times epsilon. Why? Because remember here we have epsilon equal to magnitude of L1 minus L2 by 2. So 2 we take it to the other side, we end up with magnitude of L1 minus L2 is equal to 2 epsilon. We have, because of this choice of epsilon, we have 2 epsilon is equal to magnitude of L1 minus L2. So we have arrived at magnitude of L1 minus L2 is less than magnitude of L1 minus L2. But these two are the same numbers, right? So a number cannot be less than itself. So that means it is a contradiction. Hence, we say that L1 is equal to L2, which tells us that the limit of a sequence is unique. Now let's look at the second theorem. Absolute value preserves convergence. What does that mean? If A sub n is a convergent sequence, then if we take all the terms of that sequence and take the absolute value of those terms and form a sequence, it will also be convergent. So let L equal to limit as n goes to infinity of A sub n. So L is the limit. Let epsilon be greater than 0. We can choose any value greater than 0. Since A sub n goes to the limit, there exists n in natural numbers such that magnitude of a sub n minus L is less than epsilon for all n greater than n. So then for all n greater than n, we have magnitude of a sub n minus magnitude of L is less than or equal to the magnitude of a sub n minus L less than epsilon. Thus, limit as n goes to infinity of the magnitude of a sub n is equal to magnitude of L. The sequence of magnitudes of a sub n is convergent. Here we have a sequence whose terms are the absolute values of the original sequence. So if the original sequence is convergent, then this is also convergent. But remember, converse is not. If the sequence made up of absolute values of a sub n is a convergent sequence, then the sequence formed by a sub n need not be a convergent sequence. So that was our second theorem. Absolute value preserves convergence. Every convergent sequence is bounded. That means it has a lower bound and an upper bound. So limit as n goes to infinity of a sub n is equal to L. Let's take epsilon equal to 1. We can take anything. Then there exists n in natural numbers such that magnitude of a sub n minus L is less than 1 for all n greater than or equal to n, which implies L minus 1 is less than a sub n, which is in turn less than L plus 1 for all n greater than or equal to n, which implies that the magnitude of a sub n is less than or equal to the magnitude of L plus 1 for all n greater than or equal to n. That means finite number of terms in the sequence a1 to a sub capital N is bounded, and let m be the largest of these terms, which includes absolute value of L plus 1. Then magnitude of a sub n is less than or equal to m for all n in the set of natural numbers, which means the sequence a sub n is bounded. So that was every convergent sequence is bounded. Now let's look at the next theorem. Eventual positivity when the limit is positive. What this means is that if the limit is positive of a sequence, then even if the initial terms are negative, at some point in the sequence, we will end up with positive terms. So let's see how to prove this. We have L is equal to limit as n goes to infinity of a sub n is greater than 0. So we have here limit is positive. So let epsilon be equal to L by 2. Since this is positive, that means L by 2 is also positive. By convergence, we have there exists m in natural numbers such that the magnitude of a sub n minus L is less than L by 2 for all n greater than m. Then for all n greater than m, we have a sub n is greater than L minus L by 2. And L minus L by 2 gives you L by 2, which is greater than 0. Eventually, all terms of the sequence are positive. So here you have to be clear. Eventually, that means after some terms, the terms become positive. So formally, we write it as if limit as n goes to infinity of a sub n is equal to L and L is greater than 0, then there exists m in n such that A sub n is greater than 0 for all n greater than m. That was our fourth theorem. Eventual positivity when the limit is positive. So here, if the limit is positive, initial terms may be negative. But as we keep going forward, it will turn positive and remain positive. If in a convergent sequence, a finite number of terms are removed from the start, the limit L will not change. Remember, here we are talking of infinite sequences, as n goes to infinity. So from that sequence, if we remove however many finite terms from the beginning, the limit doesn't change. So let A sub n be a sequence such that limit as n goes to infinity of A sub n is equal to L. Let B sub n be another sequence such that B sub n is equal to A sub n for all n greater than n naught, for some fixed n naught in natural numbers. So understand this carefully, what is happening here. We are basically removing initial n naught terms. So here Bn nth term is equal to of B is equal to the nth term in An for all n greater than n naught. So that means initial n naught terms have been removed from Bn. Let epsilon be greater than 0. Now since A sub n goes to L, there exists n1 in natural numbers such that A sub n minus L absolute value is less than epsilon for all n greater than n1. Let n be equal to the larger of n naught and n1. Then for all n greater than n, we have magnitude of Bn minus L is equal to the magnitude of An minus L less than epsilon. So hence limit as n goes to infinity of Bn is also equal to L. So therefore, removing finitely many terms from the start of the sequence does not change the limit. So that was theorems on limits of sequences. You can practice looking at sequences and trying to work out how these theorems work. Now, if you found this session helpful, please do like, share, and subscribe. Questions, suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now.